Our group consists of 4 members working together on this project. First, Alexander Koi Kai Seng with metric number CE240071. Next is me, Nur Shazani Binti Rambali, and my metric number is TE230076. The third member is Fitra Alif bin Muzamil, metric number CE220070. Lastly, Osama TK Miklik with metric number AE 2000995. Each member has contributed actively to a different part of the project to ensure its successful completion. Thank you. Hello, my name is Sasha Binti Rambali and my metric number is DE230007C. Today I will present the introduction. Magnetostatic is the study of magnetic fields that are constant with time, such as field produced by permanent magnet. In real industrial system, machine components usually use bearing for support, but bearing cause friction, wear, heat, and require lubrication. This increase maintenance and reduce efficiency. Therefore, contactless support systems are preferred in precious applications. In our project, we demonstrate contactless support using diamagnetic levitation, where a pyrolytic graphite sheet can levitate above a strong non-uniform magnetic field produced by a 2 by 2 N52 Neodymium magnet array. Thank you. And now I will present the problem statement. In most machines, bearings provide mechanical support, but they involve physical contact. This causes friction, wear, heat, and vibration and noise. Bearings also require lubrication, which increase maintenance and can cause contamination, especially in precious applications. Therefore, a contactless support method is needed in this project. We propose a simple contactless magnetic support using diamagnetic levitation with permanent magnet.
Hello everyone, my name is Fitra Ali bin Muzamil and my number card matrix is CE22070. Okay, today I want to present about the objective. Our objective are to build a simple prototype that can demonstrate contactless support using the diamagnetic levitation. We want to achieve stable levitation of pyrolytic graphite. Explain it using magnetostatic theory. Study how magnet spacing effects and levitation, height and stability, and finally relate our results to industrial applications like magnetic bearings and vibration isolation. Okay, for the scope, we focus only on magnetostatic using permanent magnets. We designed a 2x2 N52 magnet array and tested pyrolytic graphite levitation while varying magnet spacing. We measured air gap height and stability. We did not include time varying electromagnetic fields, coil-based levitation, quantum system, or FEM simulation. Okay, for the concept of diamagnetic, now I will explain the concept of diamagnetic levitation used in our project. Pyrolytic graphite is a diamagnetic material, meaning it produces an induced magnetic field opposite to an applied magnetic field. Because of this property, it will be repelled from regions where the magnetic field is stronger. In our setup, the neodymium magnet array generates a strong magnetic field. When the graphite is placed above the magnet, the repulsive force pushes it upward. Levitation occurs when the upward magnetic force becomes equal to the weight of the graphite, which is expressed as Fmag, approximately equals mg. Also, stable levitation requires a non-uniform magnetic field, meaning the field must have a strong gradient. That is why magnet arrangement is important for this experiment. Okay, for the magnetostatic. Magnetostatic refers to magnetic fields that do not change with time, such as fields produced by permanent magnets. The key parameters are the magnetic flux density B and the magnetic field intensity H, and they are related by the equation B equals mu H, where mu represents the permeability. From Gauss' law For magnetism, divergence of B equals 0, which means magnetic field lines always form closed loops and there are no magnetic monopoles. For diamagnetic levitation, the important relationship is that the magnetic force depends on the magnetic field gradient. We can express it as Fmag is proportional to the gradient of B square. So when the field gradient is high, the levitation force becomes stronger. This directly links to our experiment where we change magnet spacing because spacing affects the field gradient and therefore affects the levitation height.
Financial Ledger question CE240071. Now I'm going to design the prototype design. We use 4 N52 Neodymium magnets arranged in a 2x2 array. The magnets are mounted on a metal base and we use double-sided tape to hold them firmly so they do not move during experiment. The polarity arrangement is alternated, meaning north and south poles are arranged in an alternating pattern. This is done to produce a stronger and more non-uniform magnetic field which improves levitation stability. A pyrolytic graphite sheet is placed above the magnet array. When the position is correct, it levitates without any physical contact. Now for the methodology. The independent variable in our experiment is the magnet spacing, which is edge to edge gap between adjacent magnets. We tested spacing between values of 0, 2, 4, and 6 and 8 mm. First, we arrange the magnets in a 2x2 layout or with alternating polarity. Next, we use the spacers such as cardboard or plastic strips to set the required spacing. The magnets were fixed on a base using tape, and then pyrolytic graphite was placed above the magnet array and allowed to stabilize. We recorded whether it's levitated stability for at least 10 seconds. To measure levitation height, we use a DIY shim method because the gap is a sub-millimeter range. We use paper strips or note for as thickness was stacked and inserted until they were touched the graphite. The thickness of the stack was measured and recorded as the levitation height. We repeated each measurement 3 times for reliability and then calculated average height. And this is our results for table levitation height versus magnet spacing. For each spacing value, 3 trials were taken and the average levitation height was calculated at 0 mm spacing, which means the magnets are touching. We obtained the highest average air gap, which is 0.97 mm, and then the levitation height was stable. At 2 mm spacing, the average height was decreased to 0.77 mm, but levitation remained stable. At 4 mm spacing, the levitation height further decreased to 0.60 mm, still stable. At 6 mm spacing, the levitation became lower and more sensitive with an average height of 0.37 mm. Finally, at 8 mm spacing, the levitation fell completely with 0 mm height and stability was unstable. Therefore, our results shows a clear decreasing trend where levitation height decreases when our magnet spacing increases.
Hello everyone, I am Osama. Today I would like to present the discussion. From the theory, we know that the magnetic levitation force depends on the magnetic field gradient, which is F mag proportional to gradient of B squared. When magnets are close together, the magnetic field becomes stronger and the gradient is higher. This produces a stronger repulsive force of the graphites, resulting in higher levitation height. When the spacing increases, the magnetic field becomes weaker and gradient reduces threshold. The upward magnetic force decrease and levitation height reduce. This explains why 0 mm spacing gives the height elevation height and why at 8 mm spacing elevation could not occurs because if mag becomes similar than milligram, so the crevice cannot lift it. In terms of industrial application, this concept is related to the magnetic spring system, vibration isolation platforms, and support system that reduce confirmation and shear everywhere because it reduces friction and remove need for liberation. To conclude our project successfully demonstrating contested magnetic support system using dynamic levitation, we showed that pyrolytic graphics can levitate stably above 2 times magnetic array to the magnetic resolution. The experiment confirmed the magnet spacing significantly affects levitation height. The maximum levitating height was 0.97 millimeter at 0 millimeter spacing, and levitation field at 8 millimeter spacing. This supports magnetics theory where magnetic force depends on the field gradient and deviation occurs when the magnetic force balances gravitational force. That's all. Thank you so much.
I'm Alexander, going to show you about our project demo. So this is our magnet N52 magnet array 2x2. This is our base, metal base. This will be our graphite, pyrolytic graphite. This is our shim, which to measure air gap between the pyrolytic graphite and magnet levitation air gap. And this is our digital clipper to measure each spacer between our magnet. So let's see, this will be roughly 1 millimeter for one cardboard. And now we're going to measure the air gap between pyrolytic graphite and our magnet N52. So as you can see, before this I've measured our air gap between this without any spacer is 0 millimeter spacer is 1 millimeter. As you can see, this is our DIY shim. Here's the end, right, 1 mm. So when we place it below, see, it touches the graphite. So when it touches, means by the air gap between both of them is roughly 1 millimeter. Okay, now we have 8 millimeter spacer, which will be then added between the magnets of each part, so we can measure whether if our graphite will levitate or not. And now for 8 millimeter spacer, we're going to see whether if our graphite still levitates on the magnet. As you can see, it isn't levitating anymore. As we know the theory, when spacing increases, then our levitation height decreases. And you can see here proves that during 8 millimeter spacer, the levitation fails. So our graphite can't levitate and there's no air gap between both of them. So in conclusion, this demo video proves that our prototype is functioning successfully. Our pyrolytic graphite levitates stably above the magnet array. So demonstrating this friction support our result matches our table graph. So where we can apply a theory where levitation height reduces with the increasing magnet spacing, and then the magnet will become unstable at 8 millimeter. And that's all for our group today. Thank you.